So here the review portions are review of magnetically coupled circuit. So the subject is transformers and generator. So that first you should know the definition of transformer and working principle of transformer and the types of transformer. After that, what are the losses of the transformer? So by knowing this as well as EMF equation of transformer and torque and efficiency and condition for maximum efficiency. So these all the things studied in first year basic electrical engineering. So let me give you some brief idea about transformer. So you all know already the transformer is nothing but it is a static device, and it will be used for transferring electric power from one place to other place by changing voltage and current but without changing the frequency. So here it works on the principle of electromagnetic induction. Also you can say it as a mutual induction. So mutual induction or electrical induction is nothing but uh, if the supply is given to the primary side of the transformer, it will be induce EMF in the secondary side of the transformer. So that's what we can call it as mutual induction. So you can see here. hmm, So it consists of two coils. You all know these basics. So here there are two coils. One is a primary winding. So it will be having the primary winding connected across the AC supply, and secondary winding which is connected across load. So always the secondary winding which is connected across load and will be giving supply to the primary side of the transformer. So that the supply, if it is a single phase transformer, the supply is single phase is 230 volts. If it is a three phase transformer, the supply is 440 volts. So some basics I am trying to explain you. So it works on the principle. I think are you, can you see this arrow?
Oh, yes, sir.
Yeah. So just see here, AC supply is given to this primary winding of the transformer. So when the supply is given to this primary side of the transformer, current starts to flow through this primary winding of the transformer. Due to the flow of this current, the magnetic flux which will be produced in a primary winding. So this flux will be going to link with the secondary side of the transformer. So due to this linkage of the flux, the current which will be induced in the secondary side of the transformer, that will be flows through the load. So that we can call this as secondary winding of the transformer. So similarly, this is the types of transformer. Two types of the transformer. One is a core type of transformer, the one is shell type of transformer. So here the core type of transformer is a rectangular type, and the shell type of the transformer, the difference between these two are here will be having two limbs. So this is the first limb and this is the second limb. The two limbs which will be having in core type of the transformer. Similarly, three limbs will be having in a shell type of the transformer. And here winding surrounds the, or else the windings encircle the core. Here the core encircle the winding. See here. So these are the core. This will be encircle the windings in the case of shell type of transformer. Here the windings surrounds the core. And in case of core type of transformer, natural cooling is possible. Here there is no natural cooling. Have to use the types of cooling method. Will come in the next concept. So this is about core, and there will be two types of losses. One is iron loss and copper loss. So iron loss we can also call this as a core loss. Why we can call this as iron loss means the loss is nothing but the heat dissipation. So whenever the supply is given to the transformer, the current starts to flow in a core of the transformer. Due to that continuous supply of current, the core will get heats up. So that heating effect we can call it as losses. So the core is made up of iron, so that the losses which appears in core we can call it as iron losses. Similarly, the winding losses, windings which are made up of copper, so that the heat which will be produced in the winding we can call this as copper losses. So again, in case of hysteresis loss and eddy current losses, there are the two types of iron losses. So hysteresis loss is due to magnetization. So magnetization and demagnetization is nothing but the whenever the supply is given to the core of the transformer, so it will be starts to magnetizing, it will be starts to producing the flux. So due to that linkage of the flux, the heat will be dissipated in a core, so that we can call this as hysteresis loss. These all basics you already studied in the first year. I'm just glance the concept of what and all you studied. Similarly, eddy current losses. So this will be produced due to eddy currents, and copper loss is nothing but I square R losses, which will be produced in the primary side of the transformer winding and secondary winding of the transformer. And total copper loss is nothing but I1 square R1. 1 is nothing but primary and 2 is nothing but secondary. I1 square R1 is nothing but primary side copper loss. I2 square R2 is nothing but secondary side copper loss. So these are some.
Sir. Sir.
Yeah. Tell me.
Sir.
Yes.
The previous page, sir.
Sorry.
That R01 and R02, why is that, sir?
Yeah.
The
This,
previous page, sir, R0, there's copper loss.
Here R01
Total
and R02,
copper
right?
losses.
Yes.
There,
R01.
we have written. Yes. First it is R1 and R2. Why it is R0 again?
Yeah, I'll clarify that. So R1 is nothing but primary side of the resistance. Primary winding and secondary winding you have, right? So primary side will be having, I'll just clarify one thing. Where there is a resistance, there is a loss. Audible? Can you hear?
Yes.
Where there is a resistance, there is a loss. So it will be having two windings. One is primary winding, other one is a secondary winding. So this 1 degree is nothing but primary winding and 2 degree is nothing but secondary windings. So why I'll be writing R01 and R02 is nothing but R1 is nothing but primary side resistance, R2 is nothing but secondary side resistance. If you are going to write the equivalent circuit diagram of transformer, so you have to write the equivalent circuit diagram of transformer either by referring the primary winding or else by referring the secondary winding, which is nothing but will be converting this R2 in terms of primary resistance or else R1 in terms of secondary resistance. So here the total copper loss is nothing but I1 square R01. So this R01 is nothing but the equivalent resistance, two resistance as I told, one is primary resistance, other one is secondary winding resistance. So the equivalent resistance of transformer by refer to the primary side. One is nothing but primary. Similarly, if you're considering the secondary side, so I want to write the resistance in terms of secondary side. Okay. So in that case, I2 square into R02, 02, R02 is nothing but the equivalent equivalent resistance equivalent resistance that will be referred to secondary side. Clear?
Yes.
Okay. So these are the basics. You will get to know whenever we'll start the equivalent circuit diagram. So these all will be there in your review portion, so that I'm just glancing this basics. You can see here R01. R01 is equivalent of total resistance. Equivalent of total resistance means it includes primary winding resistance and secondary winding resistance, but it is referred as primary winding. Similarly, this AMF equation of transformer you already studied. You just look at here the clamps. So AMF equation of primary winding of the transformer and secondary winding of the transformer. So just remember this AMF equation, N1 phi m into 2 pi f, or else you can write here omega. Okay, one sec. So the total EMF equation of primary winding and secondary winding resistance is, so E1 is nothing but EMF of primary side. So this capital E1 is nothing but RMS value of voltage, and these two are written in terms of RMS values. So root means square value. RMS value, we know that VRMS equals to VM divided by root 2. So that So that E1 is nothing but RMS value of voltage is given by 4.44 F5M into N1. F is frequency and this is a maximum flux, and N1 is number of turns in primary winding. Similarly, 4.44 F is frequency, 5M is 5M is maximum flux, and N2 is the number of turns referred to secondary winding. So these are EMF equation, and turns ratio. I can write. You can write turns ratio either it as N2 by N1, that is equals to E2 by E1. These are some basics. You can see here turns ratio. If N2 is greater than N1, so number of turns in secondary winding, if it is more than number of turns in primary winding, so N is directly proportional to voltage. Okay. So N2 is greater than N1 is nothing but E2 is greater than E1. It is nothing but you can say it as a step up transformer or a step up transformer. So we can classify the transformer based on number of turns. So there are two types of transformer. One is step up transformer, the one is step down transformer. Step up transformer means stepping up the voltage from lower voltage to higher voltage. Step down transformer is nothing but stepping down the voltage from high voltage. So here step up is nothing but stepping up the voltage from lower to higher, so that E1 is less than E2, or else E2 is greater than E1. Similarly for step down, E2 is less than E1, or else E1 is greater than E2. So the relationship between current and number of turns, N2 by N1 equals to I1 by I2. So that's equals to E2 by E1. Yes.
So will they ask like EMF equation to
In
to
examination?
write everything? Yes, sir.
No. In examination, it is just a review portion, but you should know the formula and all.
Okay. Yes.
Do you have syllabus copy in your hand? Vidhi, do you have syllabus copy in your hand?
Now I don't have.
Okay, you just keep your syllabus copy for next class, okay? Then only we'll get to know.
Okay.
So these all are a review portion. So a review portion is nothing but the basics you should know. That's it. So they will be not going to ask anything in examination from this. You just have to know the basics. That's it. Then only we can understand the next concepts. And your portion starts from you can note down
No load.
silent
Yes,
silent features of ideal transformers. From here it starts. So that is ideal transformer. So first you should know that difference between ideal transformer and practical transformer. So ideal transformer is nothing but, so in ideal transformer the flux will be zero, and input voltage will be same as output voltage, and there is no losses in a transformer. The copper loss and the iron losses in a transformer will be zero in case of ideal transformer. The word itself says ideal. So here the transformer which will be null, that will be having the input power will be same as output power. So that here in case of ideal transformer, zero winding resistance and zero leakage flux, and also no losses. So this is nothing but ideal transformer. First you should know what is ideal transformer. Ideal transformer means the transformer which has zero winding resistance, zero leakage flux, and copper loss and iron loss will be zero. That type of transformer can call it as ideal transformer, and also the output power which will be same as input power. So here your portion start. Ideal transformer. First point is the silent features of ideal transformer. So silent features of ideal transformer is nothing but, so there are 4 points you should remember. First one is the ideal transformer. Why they will be? What is the features? That is the advantage of ideal transformer is, in case of ideal transformer, it has no losses. as I just told that there are two types of losses in case of transformer. One is what iron losses, and other one is copper loss. So in case of ideal transformer, the copper loss and iron loss will be zero. So that we can call this as ideal transformer. The feature is it has no losses, and also winding resistance is zero, and leakage flux is also zero, and the input voltage will be same as output voltage, that is V1 equals to E1, and sorry, V1 equals to E1, that is input voltage will be same as induced EMF in primary winding, that will be same in case of secondary winding, that is a V2 and E2, so that then there is no voltage drop, so that what you can say, so that input power which will be same as output power. So these 4 points you should remember. Okay, so the first point is no losses, second point is winding resistance is zero, and third point is leakage flux is zero, and fourth point you can write as input power and output power will be same, that is input power is same as output power, that is V1 I1 equals to V2 I2. So ideal transformer on no load. So here the main thing is that you should understand the vector diagram. Okay, so it's very easy to understand vector diagram. Before that, you have to you should understand what is ideal transformer. Then you can easily understand the vector diagram of the ideal transformer. You can see here ideal transformer. So this is ideal transformer, you can see. So here I'll be going to apply AC supply, that will be 230 volts I'll be applying. 230 volts AC supply will be going to apply, and I1 starts to flow in this winding. So this current which will be produces a flux phi, and this flux will be linked with the secondary winding of the transformer. So due to that, current which will be produces, that is the current which will be produced in secondary winding of the transformer. Hence the transformer is ideal transformer, so that there is no load in secondary winding. So it is like open circuit. In case of open circuit, current is zero, so that the output power is also zero. And one thing you should remember, that whenever there is a supply voltage, the induced EMF will be produces. The EMF which will be produced in primary winding as well as secondary winding of the transformer. So there are two EMF, one is E1, other one is E2. That is EMF which will be induced in the primary winding of the transformer, and EMF which will be induced in secondary winding of the transformer. So here, so if you will be if you'll be considering if you want to get the relationship between the voltage and EMF. Okay, so voltage, it will be equal to the opposite sign of the EMF according to Lenz's law. So what this Lenz's law states that uh, induced EMF opposes the cause producing it. So suppose if the induced voltage is V1, you can see here, if the induced voltage is V1, so this is V1, the applied voltage which will be cause opposite to the induced EMF. This is the direction of V1. At the same time, this will be the direction of E1. You can see here, the both direction will be opposite. So that the Lenz's law says that, the Lenz's law which states that the induced EMF opposes the cause producing it, which is supply voltage V1. Hence, E1 which will be antiphase with the V1. So you can see here V1 equals to minus E1. So if you're going to draw the vector diagram, this will be the 4 quadrant, you know. So here the first quadrant, this will be x-axis, here it is positive, here it is negative. Similarly, here it is positive and negative. So V1 equals to minus E1. So V1, E1 are same, but E1 is opposite direction. So that how can write, if the V1 is here, the E1 which will be same as V1, E1 which will be same as V1, but it is opposite to this V1. So that first what we are doing, we will be taking flux as reference. Any doubt, Vidhi?
No, sir, no, sir.
So first we can take flux as a reference, okay, while drawing the what the phasor diagram, alpha is the reference is flux for this. You can take anything as a reference, but by taking flux as a reference, this is a reference axis. So here the primary draws a current I1. You can see here the primary current which draws. So give me one sec. One second, Vidhi.
Yes, yes.
Can you hear now?
Yes, sir.
Okay, sorry for the interrupt. So here you just consider. So this is ideal transformer. Okay, so just consider the ideal transformer on no load. Consider ideal transformer on no load. So for this no load, the supply voltage set as V1. So I'll be going to applying supply voltage, that is V1, and it will be having no load, so that current flows through the secondary winding is 0, so that I2 equals to 0. So now the primary current, so now I'll come on this primary side. Wait, I'll zoom in. So for this primary current, okay, so I1 is current flows to the primary winding, so it is just necessary to produce flux whenever current starts to flow in primary winding of the transformer. So due to this I1, the flux phi will be produces. Flux phi will be produces. So as this flux will be magnetizing the core. So this is the core of the transformer. Whenever the supply is given, current starts to flow in a primary winding of the transformer. So due to this flow of primary winding of the current, that is I1, the core will be started to magnetizing. So due to that magnetizing effect, the flux which will be produces, so that it is called as magnetizing current. So current flows with this here, this I1, I can call this as magnetizing current. So I can call this I1 as magnetizing current because this will be necessary to produce a magnetizing flux in a core. Similarly, as a transformer is ideal, the winding resistance is also 0, so that it will be purely inductive in nature. So the resistance is 0. There are three types of load, as one is a resistive load, other one is inductive load, and the one is capacitive load. So when the resistance is 0 means either it is inductive load or else capacitive in nature. So I can consider this transformer is purely inductive in nature, L. Okay. By considering this winding resistance is 0 and it is purely inductive in nature, so that the magnetizing current Im is very small, which lags behind the voltage V1. Now I'll come to this, what the phasor diagram. So here, uh, first, the first point of this phasor diagram is take the reference. So here the reference is flux, so that I'll draw the reference first. So by taking this flux phi as a reference, this will be the reference. So Im equals to I naught. I'll come to this Im now. So Im is nothing but I1 now, because I2 is 0 as there is no load. So that Im is nothing but I1. I naught is nothing but no load current. There is no load, so that current flows to the primary winding is no load current. You can also call this as magnetizing current. So this Im is responsible to produce this flux. Okay, so that this Im is in phase with the flux. Understanding?
Yes, sir.
So
Yes.
this Im is responsible to produce the flux, so that by taking flux as a reference, Im is in phase with the flux. The first point is flux is the reference, and second point is Im is in phase with the flux. Im is nothing but magnetizing current, so that will be responsible to produce the flux, so that Im represent magnetizing current. So now the flux links with the both winding produces the induced EMF. You can see here. So this flux phi is links with the secondary winding as well, so that it produces two EMF. One is E1 and E2. That will be nothing but primary and secondary winding EMFs. According to Lenz's law, V1 equals to minus E1, so that E2 also opposes the V1. So hence E1 and E2 are in phase with each other. Why it is in phase with each other? Because there is no load. So E1 equals to E2. That is so that I can write here, I can draw here, as the load is inductive in nature. First step is phi as a reference. Second step, Im is in phase with the phi. Third step is this V1 lags the, sorry, Im lags the V1 at an angle of 90 degree. Im lags V1 at an angle of 90 degree. So the direction is anti-clockwise direction. You can see here, flux is a reference. Im is in phase with the flux. Third point is Im lags V1 at an angle of phi. As we know, this VE1 and E2 are in phase with each other, but it will be opposite to the V1 according to Lenz's law, so that this E1 and E2 are in phase with each other and opposite to the V1. And this is the phasor diagram for ideal transformer. Any doubts, Vidhi?
The E1 and E2, sir. The
Okay.
thing, it is opposite to V1.
Yes.
But how did we get E1 and E2 in same line?
This is ideal transformer. Okay. So this is ideal transformer. As I said, if the transformer is ideal, listening, if the transformer is ideal, V1 is the same as E1. V1 is same as E1. That is the input voltage that will be same as EMF induced in primary winding. Similarly, output voltage same as EMF induced in secondary winding. So here there is no load, but voltage V2 here. Here also V2. But V2 and V1 are same because it is ideal transformer. For example, if the V1 is 230 volts, V2 is also 230 volts. At the same time, E1 is also 230 volts and E2 is also 230 volts. Why they were writing here means some variation of the voltages, so that here V1 equals to V2. V1 equals to V2. This will be opposite to the EMF induced in respective windings, that is in the primary winding and secondary winding. So these are in same phase because the voltage which will be induced will be same, so that E1 and E2 are in phase with each other. Fine.
Yes, sir. Yes.
So this is for ideal transformer.
Right.
And this phasor diagram will be base for the upcoming phasor diagrams. So now just see once again, I'll just explain this phasor diagram. You just listen once again. So the first step is reference. Here the reference is flux. Flux phi is a reference. So this is a reference. Flux phi is reference. So which is responsible to produce flux? I1. So I1 is nothing but, so I1 that equals to Im that is equals to I naught. So Im is responsible to produce flux, that is nothing but, so that I can call this I1 as magnetizing current. So this is nothing but magnetizing current, or else you can also call this as no load current. So these two currents, these currents are responsible to produce flux, so that Im is in phase with the flux phi. Im is in phase with the flux phi. So the second point is Im is in phase with the flux. Third point is Im lags V1 at an angle of 90 degree. And fourth point is E1 and E2 are in phase with each other, but it will be opposite to the V1. This is the phasor diagram for the ideal transformer. I hope you're writing the phasor diagram.
Yes, sir.
Yes. And the next is a practical transformer on no load. Can note down, this is important. They may ask practical transformer on no load, or else practical transformer on load. Anyone they will ask in examination, either it is on no load or else it is on load, practical transformer. So ideal transformer is different, practical transformer is different. Understanding, ideal transformer is nothing but, so in case of ideal transformer the resistance value is 0. In case of ideal transformer there is no losses. In case of resistance, in case of ideal transformer, V1 equals to E1, V2 equals to E2. But in case of practical transformer it is different. Okay, here there is a resistance, here there are losses, here there's a input power and output power. Okay, understanding. So that is nothing but practical transformer. So ideally is nothing but zero, everything will be zero. But in case of practical transformer, the losses are there, and also the flux will be there, and also there will be a power, input power and output power will be there, and magnetizing component will be there. So coming to this practical transformer on no load. So here you should know that practically primary winding has certain resistance, so that I can call this as practical transformers. So you can see here, so they were not here they were sorry, here they were not given the resistance and inductances here, but practical transformer is nothing but there is a loss. Where there is a loss, so when it will be produces loss, where there is a resistance, where there is a resistance there is loss. In case of ideal transformer there is no resistance, so that there is no loss. In case of practical transformer there will be a resistance, so that there will be a loss. So there will be a resistance, so that it will be produces the heating effect. Due to that heating effect, it will be produces loss in core as well as winding. So that here the iron loss is also produces, and copper loss. So now here you can see no load input. One sec. The PDF is visible.
Yes, sir.
They will be asking this question for 6 to 8 marks in examination. The question will be like, explain the operation of transformer on no load, giving its vector diagram. Explain the operation of transformer on no load, giving its vector diagram. As a question, they will ask practical transformer on no load. So here there is no load. No load, the word is in heading itself they are telling. So this is a practical transformer, but there is no load. So where you are connecting load? On the secondary side. If there is no load, if there is no load means the secondary winding will be open. So that current flows to the secondary winding is zero, because there is no load on primary transformer. I2 is 0. Okay. So now the no load input current I0 has two components. So now I2 is 0. So this is the input current I1. So I can tell this no load input current, no load input current. So no load input current I can represent as I0, I0 as no load input current. That is nothing but your I1. So I can call this I1 as no load input current I0. It is having two components now. So this no load current will be having two components. That is, this I1 is having two components. So one is, the first component is a resistive component, also purely reactive component. That is nothing but IM. So you can see here, this no load current I not having two component. One is the purely reactive component, that is nothing but IM. This you can call this as magnetizing component of no load current. Magnetizing component of no load current. So what is the function of this magnetizing current, magnetizing component of no load current means, so this IM is responsible to produce flux. This IM is responsible to produce flux. So there, this is also called wattless component. Wattless component. Understanding with the,
Yes, sir.
there are two components in no load current, that is I naught. One is IM. IM is nothing but magnetizing component of no load current. This will be the function of this IM is, it is required to produce the flux, so that we can also call this as wattless component. First one is reactive component and the second one is active component. We can call this active component as IC. IC is nothing but active component which supplies total losses under no load condition. Remember, total losses under no load condition, because there is no load in practical transformer. As the heading says, practical transformer on no load we are studying, because there is no load, so that the no load component will be having, the no load current will be having two components. One is IM, which is responsible to produce flux. So IM is nothing but your reactive component. Also you can call this as magnetizing component. And second one is active component. It is nothing but the total losses under no load condition. Total losses under no load condition. And it is also called as power component. Power component. So practical they can call this IC as core loss component. C represent core loss component, so that I naught will be having IC plus IM. This point clear?
Yes.
If you have any doubts, you can discuss it. Don't, you can ask if you're not understanding. Okay.
Yes.
So now, can you tell me what are the two components of no load current?
Magnetizing component and core loss component.
IM and IC. What is the
IC.
yeah? What is the function of IM here?
IM produces flux.
IM produces flux. And what is IC here?
Flux. IC total losses under no load condition.
Yes, it is nothing but total losses under no load condition. So that I can write here I naught as IM plus IC. Clear?
Yes.
Okay. So now total no load current I naught is nothing but vector sum of IC and IM. So this is the total no load current. So it is nothing but I1 only. Don't be confused like I1, I0. So here I1 is nothing but current flows through the primary winding. But here there is no load, so that I2 is 0. So I can call this I1 as no load primary current. Okay. Also you can call this as no load component. So no load current you can denote it as I0. So I naught will be having two components. One is magnetizing current, that is IM. Other one is core loss component, that is IC. Okay. Hence there is no load in secondary winding, so that there is no copper loss in secondary winding. That is, copper loss in secondary winding is 0 and in primary winding is less. There is a copper loss in primary winding. but the less amount of copper loss will be there in primary side, but copper loss in secondary winding will be 0 because it is no load condition. Okay, so now we start the phasor diagram again. Very important. You have to understand the phasor diagram, then only it is very easy to write in examination rather than by hiding or practicing. So now here again we'll start with the flux. So what is the first point here? The first point is a reference. First point is reference. So I can take flux as a reference, so that the first point is reference, the flux as a reference. I hope you are drawing the phasor diagram.
Yes.
So flux is a reference. First step, the reference is a flux, that is phi. So now, which is responsible to produce flux here? Im is responsible to produce flux, that is magnetizing component is responsible to produce flux, so that Im is in phase with the flux phi. Okay, and the third step is V1, that is Im lags V1 at an angle of 90 degree. So in practical transformer, due to winding resistance, okay, the winding resistance, no load current I0 is no longer at 90 degree with respect to V1. So that Im is perpendicular to the V1. I1 is perpendicular to the V1. Hence, here I can consider the load is, by assuming the load as inductive load, current lags the voltage at an angle of 90 degree. By assuming the load as inductive load, the I1, that is Im lags V1 at an angle of 90 degree. I1 lags, Im lags V1 at an angle of 90 degree. So that here, this is the third step. Next, next is IC. So look at the IC here. Why we'll be writing IC here means IC is in phase with the V1 they were written. So why IC is V1 with respect, IC is in phase with V1 means, as I told, here the secondary side is open, so that there is no core loss in secondary winding. Okay, so the core loss which will be present in primary side, so that will be with respect to V1, so that IC is in phase with the V1. IC is in phase with the V1. So the first point is the reference is flux phi. Second point is Im is responsible to produce flux phi, so that Im is in phase with the flux. Third point is, so Im lags V1 at an angle of 90 degree. And the fourth point is IC is in phase with a V1. And the fifth point, we have to write what? The no load current. So as I told, no load current is nothing but it will be given by Im plus IC. So that you have to do here vector addition of Im and IC. So that by adding this Im and IC, you can get I0. So how will be adding Im and IC? So from the tip of IC, draw a line. This will be parallel to the Im. Similarly, from the tip of Im, draw a line which is parallel to the IC. So this is nothing but your vector addition. So here you can get what? IC. IC is nothing but Im plus IC. And the next is again V1 equals to minus E1, so that antiphase with a V1. E1 is antiphase with a V1, and E1 and E2 are in phase with each other. So either E2 is greater than E1 here, or else E1 is greater than E2 here, so that you can write either here or here E1 and E2. But the thing is that E1 is antiphase with a V1. That will be opposite to the V1, and E1 and E2 are E1 and E2 are in phase with each other. Okay, so this is the phasor diagram. Any doubts, Vidhi?
No, sir, no. Oh, just that I not
Okay.
yeah, with that lagging portion. I didn't find.
Sorry, I'm not getting.
Can you explain that, sir?
Which one?
I not that part.
How we'll be getting I note?
IC plus IM.
Okay.
Yes,
Yeah.
sir.
Okay. See, what you know here, I naught is nothing but I am plus IC. That you know, right? So while drawing the phasor diagram, I want to get I naught. So to get I naught, I have to get two components. What are those? One is magnetizing component, other one is core loss component. So magnetizing component, I have magnetizing component here, that is IM, which is responsible to produce flux. That will be a magnetizing component IM I have. Similarly, core loss component I have IC. IC is in phase with a V1 because the second winding will be the core loss in, sorry, there will be no loss in secondary side, so that I can consider IC is in phase with the primary side of the voltage V1, so that IC is in phase with the V1. So this you understood.
Yes, sir.
And next, what you know, I naught is nothing but no load current. So no load current is nothing but IC plus IM, or else IM plus IC. So I want to do addition of two vectors. So these are the vector components. So I want to do addition of two vector components. How will be adding? So from this tip of IC, this is IC, right? From the tip of IC, draw a line which is parallel to the IM. So IM is here. So draw a line parallel to the IM from the tip of IC. Similarly, from the tip of IM, draw a line which is parallel to the IC. It will be intersect one side. Okay. So this is nothing but your I node. By adding these two, you can get what? I node. So this will be
I
the
know.
I node. Clear now?
Yes, sir.
Can you explain this phasor diagram? Like,
Yes, sir. Oh, first we have to give the reference axis.
yes.
Reference, that is phi.
Hmm.
Then IM, which is in phase to phi.
Hmm.
IM is nothing but I1.
Hmm.
And then the V1, which is IM lags V1
At an angle of 90 degree.
90 degree.
Hmm.
Then IC, which is in phase to V1,
Hmm.
drawing that. Then we are getting the I naught, which is no, not perpendicular. IC, which has two components, IM and IC.
Hmm. You don't
Yes,
confuse
and
with
then E1
the.
and
No, you don't confuse with I1 and all. Here there is no I1 only. Okay. I1 is nothing but I naught here. See, this I1 is nothing but I naught here. In case of
yes,
ideal
yes,
transformer, I1 equals to IM. In case of ideal transformer, this is practical transformer. So that here I naught is nothing but I1. Okay. This is. So I want to get primary side current here. Primary side current is nothing but I1 I want to get. So what is I know I1 or I naught here? IC plus IM. So I'll tell you once again, just observe clearly. First step is reference. Phi is a reference. Okay. Second step is IM is in phase with the phi because IM is responsible to produce flux. So that IM is in phase with the flux. And third step is IM lags V1 at an angle of 90 degree. IM lags V1 at an angle of 90 degree. And fourth step is IC is in phase with the V1. IC is in phase with V1. And fifth step is by adding IM and IC I can get I naught. By adding IM and IC I can get I naught. So this is a vector addition of IM and IC. I can get I naught, and angle between V1 and I naught is phi naught. That is no load angle. Angle between V1 and phi I naught is phi naught, and V1 and E1 are equal and opposite, so that E1 is anti-phase with a V1 and E1 and E2 are in phase with each other. Clear?
yes.
Can you explain?
Oh, yes, sir. Oh, first we are getting the reference angle, that is phi,
Okay.
which Im is the cos which produces phi. So it is in phase to phi.
Hmm.
Then Im lags V1, which is perpendicular.
Hmm.
Then IC is in phase to V1.
Hmm.
So then Im, that is magnetizing current, and core loss, the addition of that will give I naught.
Hmm.
Then E1 and E2, which is in opposite to
Hmm.
V1.
Hmm. Clear? Any doubt? If you have any doubt, you can
And
ask.
oh no, sir.
Okay. So now, with the help of this phasor diagram, what we are doing? So we want to write a value of IC and IM with the help of this phasor diagram. So how will be writing IM and how will be writing IC? So this is IM and this is IC. So I have to write velocity components of IM and IC. Velocity components as you studied in the elements of civil engineering. So here the angle is phi naught, okay, and the value of this is I naught. This is I naught here. This is I naught and angle is phi naught. I naught it is. So how will you write IM? Do you know anything about this velocity components?
Uh, yes, sir. That cos and sin Im is
Yes,
equal to
yes.
sin omega t.
How will write this IM? IM is given by, so this IM I can write here it as IM equals to I naught into sin or cos. Angle is phi naught. Im equals to I naught into sin phi
Sin.
naught. Sin phi naught. I naught into sin phi naught. Similarly, how will write IC?
I naught cos omega. I naught cos phi.
I naught cos phi naught. Just
Phi
note,
naught.
yes, you just note it down in your notes. The value of Im is nothing but I naught sin phi naught. Similarly, IC is nothing but core loss component is given by IC equals to I naught cos phi naught. I naught cos phi naught. These are the velocity components that you studied in your elements of civil engineering. I naught cos phi naught. So with the help of this, I can write input voltage now. Output side is zero. There is a, sorry, power. I'll come to the power now. So the I2 is zero, so that secondary side there is no power. I can write. So if the load is not connected on the secondary side, so only which produces core losses, as you studied in the open circuit and short circuit test. Can you remember? So while doing the experiments of open circuit test and short circuit test, if the secondary side is open, we'll be applying the rated voltage and noting down the V1, I1 and W1. Whereas the core loss will only, which there will be only core loss only present in a transformer when there is no load. If there is a load, or else if there is a short circuit, if you are doing the short circuit here, then there will be only copper losses. Here it is a open, here it is a no load condition, so that I2 is 0, so that there is no copper loss, only core loss will be present in case of practical transformer on no load. So that I can write here the only core loss is present here. I'll write here C. Only core loss will be present. Hence, there is no copper loss. Only core loss will be present. So that I can write power, that is W naught is nothing but no load power is given by uh, no load power is given by V1, that is input voltage is nothing but V1 here. The supply voltage is V1 into current flows to the transformer is I naught here, that is a no load current, V1 into I naught into cos phi naught, into cos phi naught is the power of practical transformer on no load. Power of practical transformer on no load is nothing but W naught equals to V1 I naught cos phi naught, whereas there is no copper loss, so that you can write this is nothing but your copper loss. Sorry, this is nothing but your iron loss. Iron loss. Clear? Any doubt with the?
No, sir.
Okay. So this is of practical transformer on no load. So today we just discussed some review portion, that is some basics of transformer and losses of transformer and types of transformer, EMF equation of transformer. Do you know the condition of maximum efficiency?
No.
Condition for maximum efficiency?
No.
That you did some derivation in the first year. Iron loss equals to copper loss. That is Wi equals to Wc. Can you remember in the first year while doing?
Yeah. Yes, sir. I
Iron,
remember only the equations.
yeah, iron loss equals to copper loss will be the condition for maximum
Copper
condition.
loss.
So they will ask anyone either practical transformer on no load or else a transformer on load. Okay. So anyone they will ask in the examination, so that whenever writing this explanation for practical transformer on no load, first you should draw the transformer like you have here, and you write the notation and you have to explain two components. That is I not having two components. One is reactive component, nothing but IM is called as magnetizing component of no load current, and you have to write the function of this no load current required no load current function of IM that will be responsible to produce the flux. And also you have to know that for IM they'll be having two names. One is magnetizing component of no load current and other one name is wattless component. Similarly, for IC, you have two names. One is power component, other one is core loss component, IC. And you have to remember that expression IM equals to I naught sin phi naught and IC equals to I naught cos phi naught. And you have to remember the steps to draw the phasor diagram of practical transformer on no load and ideal transformer on no load and features of ideal transformers. Features of ideal transformers is nothing but resistance is zero, leakage flux is zero, and also the power is zero, and there is no current flows to the second side of the transformer. So you can see here the steps they were written to draw. This you written right? IC and IM, the values of IC and IM.
Yes. Yes.
You also write this under no load condition, the power input equals to the iron loss or copper loss is only iron loss it is because the second side is open.
No, the one you gave W not equal to V1. I
Yes,
not
yes,
cos
yes,
phi naught.
yes. You can write W naught or else WY. That is you
Yes.
just to write your convenient word. WY sometimes they will call it as W naught. Sometimes they will call it as WI. I is nothing but iron loss. W naught is nothing but on no
Yes.
load.
Yes.
So this practical transformer on load will do in tomorrow class.
Yes. Sir, for ideal it is not there, sir. Ideal only no load. On load is there.
No. In ideal there is no on load because ideal transformer is nothing but no load. Ideal transformer is nothing but there is no load.
Yes.
So that only no load condition in ideal transformer. But in practical transformer, there will be no load and on load. So after that, we'll be having a phasor diagram on load. That is very important. I'll explain how to draw that and how to remember that. And after that, we'll be having equivalent circuit of transformer. I'll tell you how to draw and how to remember equivalent circuit diagram. So in this first chapter, just remember that you have to concentrate on this practical transformer on load and no load. Okay, and that too with phasor diagrams
Yes.
of practical transformer on load and no load, and also equivalent circuit, OC and AC test. Okay, so they will ask any of two questions. Either they will ask practical transformer on no load, or else practical transformer on load. Out of these to any one. Also, they may ask this one equivalent circuit diagram of transformer, and also they will ask OC and AC test. OC and AC test, the explanation whatever will be having in your lab, no lab manual.
Mm.
The same thing you can write, no problem with that. Also, I'll give that word to write. And once you finish this alt efficiency, and I'll explain some this voltage regulation and significance, then we'll solve some problems. You practice that problems, they may ask problems also. Okay, then this
Yes.
three-phase transformers, it is very easy. I'll explain you. We only will be having some 5 connections. You have to practice. Only the thing is that you have to do practice and you have to do remember. If you are trying to by hearting the equations, means you won't remember. Only you have to understand, you have to practice, then you have to speed up your handwriting. That's it. Okay. Tomorrow
Yes.
at what time you'll be able?
Same time.
Same time. Tomorrow shall we
Yes.
extend to 1.5 hour, 3 to 4:30? Also,
Uh,
1 hour is enough. You tell your convenient way.
okay, sir. 3 to 4:30 is okay.
Yeah. Okay. Fine then.
Yes.
Okay.
Okay.
Chalo,
Thank you.
then have a nice evening. Bye.
Thank you.